All right, in this series of videos, we're going to take a look at alkenes. These are compounds that contain carbon-carbon double bonds. They're often referred to as unsaturated hydrocarbons. The unsaturation means that they don't have their full complement of hydrogens because we now have removed two hydrogens to make that carbon-carbon double bond. These always adhere to the molecular formula C to the N, H to the 2N, where N equals the number of carbons. So this molecular formula, C to the N, H to the 2N, will exist when we have molecules that have carbon-carbon double bonds. So let's just look at a simple example of this. So here we have a 3-carbon compound, but now we have a double bond indicated here. So at the end, let's just go ahead and put in the fact that there would be 2 hydrogens here. Okay, so that carbon now has 4 bonds to it. This carbon would have 1 hydrogen attached, and then this carbon, because it's bonded through a single bond, would have 3 hydrogens. And when you're first learning these compounds, it's totally okay to draw in the carbons on a line angle structure and also add in the associated hydrogens. So as you might expect, we've talked about this before, carbon-carbon double bonds dictated a definite shape to an alkene, and that shape is going to have a 120-degree bond angle. So this part of the molecule is going to be flat, trigonal, and planar. Conversely, this carbon, because it's bonded through single bonds, this would be tetrahedral. But the bond angles surrounding these carbons all over here, these are all 120 degrees. So alkenes, or unsaturated hydrocarbons, at least that portion of a molecule is going to be flat. All right, and let's just verify. Let's just go back through this here to make sure that it does adhere to that formula. This is carbon 1, 2, and 3. So I have C3. And if this formula is correct, I should only have 6 hydrogens. Well, we drew them out up above. I had 1, 2, 3, 4, 5, and 6. So this molecule would adhere to that molecular formula, C3H6. So when it comes to alkenes, one of the keys is making sure that you always remember that carbon's going to have 4 bonds. And again, we're not showing this extra hydrogen here, but you have to remember that it's implied. So the alkene, as we draw it here, is kind of a very simplistic way to draw a carbon-carbon double bond. There's actually quite a bit more to it. So if I were to take this molecule and sort of zoom in on the carbon-carbon double bond and actually look at what the bonds actually look like, let me sort of draw a picture of what the molecular orbitals actually look like in this case. So when you have a carbon-carbon double bond, and I'll redraw this same molecule, I'm going to put the methyl group sort of sticking out this way, and my hydrogen going to the back. So that's going to be this hydrogen coming off carbon 2. So this is carbon 3, 2, and 1. Over here, I'm going to have my 2 hydrogens coming off carbon 1. What's actually going on here? Well, there are actually 2 types of orbitals that are going to make up a carbon-carbon double bond. So in one case, I'm going to have a set of orbitals that are going to overlap. They're going to share electrons in sort of a head-to-head interaction. And this type of orbital is called, or this overlap of 2 orbitals is called a sigma bond. Okay, and this is the traditional covalent type of bond that we would have at any of these other positions where we just draw a line or a wedge or dash. It's the head-to-head overlap of 2 electrons being shared. That's called a sigma bond. But when it comes to alkenes, they have another type of orbital that's going to allow the overlap of 2 electrons, and these are very different. They have a shape that looks like sort of these 2 dumbbells coming off of each of the carbons, and in each of those orbitals there's a single electron. Okay, these orbitals are called pi orbitals. And if we have 2 pi orbitals next to each other on 2 adjacent carbons, those 2 electrons can actually be shared through space. And it's actually being shared both above and below the plane all at the same time. So these electrons are oscillating back and forth. They're being shared. However, because of the distance between those orbitals, this type of bond is not going to be nearly as strong as a sigma bond. So this type of bond is called a pi bond. And it's this type of bond, the fact that these electrons are sort of above and below the plane defined by the atoms here, and the fact that this pi bond is not nearly as strong as the sigma, this is what's going to dictate the reactivity of alkenes. Alkenes are going to be much more reactive than regular old alkanes because of the presence of this unusual different sort of pi bond. So in the next example, we're going to take a look at some of the ramifications of this particular structure. All right, so let's take a look at what the effect of having that extra set of pi orbitals and that pi bond does to a carbon-carbon double bond. So if I draw out the following simple alkene, in this format here, and then I'm also going to draw essentially the same molecule, but I'm going to orient my methyl groups a little bit differently. Okay, notice these two molecules have the same basic connectivity of carbons. Okay, so we've got 4 carbons and a double bond between carbons 2 and 3. However, in this molecule on the right, I've oriented so the methyl groups are kind of both on the same side of this bond. Well, it turns out that with alkenes, these are not interconvertible. So I cannot interconvert between these two. And the rationale or the reason for that is that this type of bond, a carbon-carbon double bond, is not freely rotatable. A carbon-carbon single bond, those can freely rotate and give rise to conformations. However, a rotation about a carbon-carbon double bond is not allowed. Let's take a look at why. So if I now draw out my pi system here that has my pi electrons, and let's put now our methyl group sticking out, and this one over here going back, and this hydrogen coming out. The presence of this pi system here, this extra bond, does not allow these 2 carbons to be easily rotated. Okay, so this extra bond essentially now defines or locks in the planarity of this molecule. So unless I could somehow break this pi bond, I can't just rotate it to give this molecule. So let me redraw this one now using our sort of pi clouds of electrons here. So this one will be coming out. And then over here, my methyl is also coming out at me. So notice here, the methyls in this case are both sort of sticking out towards you. They're on the same face, if you will, of the plane defined by these dumbbell-shaped orbitals. And again, the dumbbell-shaped orbitals, these are the pi orbitals. Those would be in the plane of the board. These 2 methyls would be coming out at you. Conversely, here we have a different orientation where one methyl group would be coming out and the other's going back. And these 2 are sort of locked in place. So I cannot simply rotate about this bond. These are not interconvertible. And these are, in fact, they're isomers. So in the case where I have the 2 methyl groups on opposite sides of the double bond, that's going to get a different name than this one where I have the 2 methyl groups on the same side of the double bond. And here's one easy way to take a look at that. If you just draw an imaginary dotted line right through the double bond. Okay, so we're just drawing it right through here. Now if I look at the fact that these 2 methyl groups are on opposite sides of that imaginary line, this molecule is now going to be called trans, we use that word trans, 2-butene. Okay, so this is a butene molecule, and the carbon-carbon double bond is starting at the 2 position, but I indicate that it's a trans 2-butene. Conversely, this 2-butene is a little bit different. The 2 methyl groups are on the same side of this imaginary line, so this is going to be called cis 2-butene. In the next example, we'll take a look at naming these and recognizing whether you have a cis or trans double bond. So let's take a look at a couple more examples of carbon-carbon cis or trans isomers. And let's see if we can do some naming practice with these. All right, so in our first example, let's just take a look at how we would name and number this. Again, we've got a carbon-carbon double bond. You always want to give the lowest numbers to the carbons involved in the double bond. This would be 1, 2, 3, 4, 5, and 6. So this is going to be a 2-hexene. Again, we put that "ene" suffix on the end to indicate that there is a carbon-carbon double bond, and the 2 is indicating the position of that double bond. However, this is not just 2-hexene. We need to indicate the fact that if we draw a dotted line, an imaginary dotted line, through the carbons involved in the double bond, notice that this methyl group and the rest of the molecule, this propyl group, are on the same side of that imaginary line. So this would be called cis 2-hexene. Let's name the next one. 1, 2, 3, 4, 5, and 6. Now I numbered it this way to give my methyl group a low substituent number and the first carbon, notice it gets a number 3. If I had numbered from the other direction, yes, I would have given a number 3 to this, but my methyl group would have had a 5 for its number. So this would be the appropriate numbering for this. And now let's go ahead and name this. I have a methyl substituent coming off carbon 2. So this is going to be 2-methyl. Okay, and then 3-hexene. But I'm not quite done yet. Let's draw our little imaginary line between carbons 3 and 4. And now let's look at what's the orientation of the substituents coming off. Well, I have this ethyl substituent coming off on one side of that imaginary line, and then I have this isopropyl group coming off the other side. So because these are on opposite sides of this imaginary line, we're going to put the little prefix trans in front. Okay, so get a little bit more practice at identifying and naming these cis-trans isomers of carbon-carbon double bonds. And please just make sure you're not confusing the use of cis and trans for double bonds with what we previously talked about, which was cycloalkanes. That can be a little confusing. They're both used. But this one, the little trick, make sure you put in this little dashed line and identify whether the substituents are on either the same or opposite sides of that dashed line. Good luck.